Good day, my name is Dan Oak and I'm a student at Athabasca University and I'm currently taking the course Computer Science 444, Embedded Robotic Programming. And today I want to talk to you guys about the nRF24L01 module, which is a wireless data transmission module that allows you to, have some fun with your microcontroller like Arduino projects. You can basically hook up two or more Arduino projects and communicate with them wirelessly, which just makes the projects a little more fun. As you can see here by the image, the module comes in a couple different varieties, starting with this one here on the right, which has an internal antenna and has about a theoretical 100 meter range. Then moving up to this one, still has an internal antenna, but it has some extra capabilities and features such as power amplification and some signal noise reduction, because these modules in general are very susceptible to signal noise, which depending on your microcontroller projects you might have a lot of, and noise from power supplies. So this just helps filter a little of that out. Still roughly the same range as this one. And then this bigger guy here boasts an external antenna and also has the additional features with the power amplification and signal noise reduction, but its main claim to fame is the external antenna, which allows it to have a theoretical range of about 1,000 meters. So 1 kilometer range as opposed to 100 meter range. So if you do a Google search of the nRF24L01 module, you're going to find lots of great information out there. But the ones I found particularly useful, so the tutorials and videos that I liked the most, were this one by How To Mechatronics, so Arduino wireless communication, nRF24L01 module. If you search that up, you'll get this nice video. It's less than 8 minutes long, and it does come with a, in the links of the video, you can go down and click and find the entire website in PDF. And the great thing about this website, it has the video still, but it has all of the images. So there's the module itself, again the internal antenna module. It has all the pinouts, just more details than the video. Again, those are the three varieties there. This one has an external antenna option as well. All the pinouts, you have the schematics, as well as you do have the code, so if you want to download the code. Another great tutorial is one by Autodesk Instructables, and same as the one by How To Mechatronics, it has both a video and the website associated with it that again has all the schematics and code that you'd want. And last but not least, there's this one by Ralph S. Bacon, titled this, and this one is a little longer. It's about a 40-minute video, but the difference with this one is this goes over a couple different codes that are associated with the module that weren't mentioned in the previous two. So the previous two by How To Mechatronics as well as Autodesk Instructables, their tutorials are fairly similar in what they're accomplishing, with some minor nuances and differences, but this video does have some things in it mentioned that aren't in the other two. Again, you don't really need the things absolutely if you're just getting started, but if you want to learn as much as possible, it's worth watching this one. Although I'd skip the first 8 minutes, as it just talks about where to buy the modules, and I mean Amazon or AliExpress or anything like that is where you get them. So what I'm going to do today is I'm just going to summarize this Autodesk Instructables tutorial. I've already read through it and created I've just highlighted key points, and I'm going to go through that with you guys in more detail and then show you one working example. Again, I recommend you still watch the actual tutorials. I'm just doing this one for the course as a prerequisite in order to post on the forum, but also just to talk about and emphasize any parts that I think are important. So I'm just going to go through this, and I've got code done up as well already from the tutorials, as well as I've got a setup here of the modules itself. So first I'll just show you, I'm using two Arduino Nanos set up individually, and each one of them is attached to the nRF24L01 modules. As you can see, I'm using the internal antenna variation, and on this Arduino on the left, I have it plugged in directly using these male to female to male DuPont cables. I have the module directly connected to the breadboard, which corresponds with the pins on the Nano. Whereas on this side, I have the module hooked up through this socket adapter, and then the socket adapter wires hook into the Nano. And for this particular project, the way I'm using it, I didn't need the socket adapter at all, because either way I've still got this mess. But the advantage of using this socket adapter would be that you basically can neaten things up, because the pinout on the modules don't allow for breadboard usage. The pins are right next to each other. You can see, and they wouldn't spread the gap here in the breadboard. So you have to plug them directly in to your Nanos via some DuPont cables or just any wires really into your microcontrollers. Whereas the socket adapter allows you to plug it into the socket adapter and then go from the socket adapter, which, depending if you're actually creating this on a project, a remote control car, or anything, this might neaten things up, as opposed to just having to zap strap a wire like I've done here. You'll also notice I have a analog joystick on this Nano, and a servo motor. That's going to be for the second example. We're going to start off simple with just transmitting some text, but that's all to come. So I'm going to go through this tutorial rather, and it is going to be probably a fairly lengthy video because I'm going to go into detail, but so just warning. I'm more or less going to focus also on the highlights, so I recommend reading the full tutorial first, and then just if you're still not quite sure, just come back here and I'll hopefully maybe expand on some things. So again, first of all, what is the nRF24L01 module? Again, it is an RF transceiver module. The word transceiver means that it can both transmit and receive. So obviously not at the same time. You're going to have to put it in transceive mode or receive mode, but it will do both. So the transceiver module will add wireless communication between two or more Arduino boards, which just makes projects a lot more fun. Again, this is the image from their website. Again, they're also using two Arduino Nanos, and they have the internal antenna versions of the RF transceiver modules hooked up through wires directly into the pins associated with the Nanos. And they don't have a joystick or servo motor here because they're for the first example, they are just going to be transmitting text. So this just shows a couple of the boilerplate data associated with it. It works on the 2.4 gigahertz to 2.5 gigahertz range, fairly ubiquitous throughout the world. Data transfer rates from 255 kilobytes per second, 1 megabyte per second, and it's cut off here, but that would be 2 megabytes per second. Very low power consumption, which is great. The operating voltage, 1.9 to 3.6. But I'm just going to click into the picture here so you guys can see it. This is again the module and the external antenna versions. Okay, so you can read that further on your own. I'm just going to go on here. So far, according to this guy, he's always used wireless communication modules between his microcontrollers, which is easy enough to do. But the problem with Wi-Fi is they're not suitable for battery operated modes. So again, we're using the nRF24L01 module. The whole reason for using this is to have wireless communication between different microcontrollers. But there is Wi-Fi modules that already do that. The problem is they're not suitable for battery operated modes because Wi-Fi modules consume a lot of current, and there's a slight delay when initiating transmission with the module when you first connect to the Wi-Fi network. So again, we're well past the days of dial-up network, but there still is that delay when you are first connecting to Wi-Fi. So with the nRF24L01 modules, you don't have those issues. So again, it is an RF transceiver module, which you can hook up to any microcontroller. I'm going to be using Arduino Nanos in this demonstration. And it is an RF transceiver. Again, that word means that it can work both as a transmitter and a receiver, hence the word transceiver. Its big claim to fame is its ultra low power compared to wireless modules. So it allows for wireless communication with ultra low power. It has 2 power saving modes. You can do 22 microamps in standby mode and 900 nanoamps in power down mode. So that's extremely low power. And the modules, so that makes the module suitable for battery operated nodes when you want these not attached to any computers and you just want them out there in the real world running off a battery pack. So very suitable for ultra low power designs. The power consumption during operation, because remember this is standby mode and power down mode, the power consumption during operation is higher at 12 milliamps during transmission, but that's still lower than powering a single LED. So still extremely low power consumption. The operating voltage is between 1.9 volts to 3.6 volts. This is important to consider. All other pins on this board are 5 volt tolerant, but the operating voltage is between 1.9 to 3.6. Now, why is this important? Well, because a lot of modules and peripherals associated with microcontrollers have an operating voltage of 5 volts, which allows us to power them off of our microcontroller via the 5 volt output. However, there is also a 3.3 volt output associated with most microcontrollers, including the Arduino line, and that's the one that we need to be powering this module off. If you try to use the 5 volts, you will ruin your module. However, luckily all the other pins are 5 volt tolerant, so you'll be fine with that. The range for these modules, again, there is the different modules, so they have different ranges, but the one used in this example, the internal antenna one, has a theoretical range of about 100 meters. However, real life conditions might lower that range. According to this tutorial, he got about 50 to 60 meters in real world conditions. Each module has 125 independent RF channels, and each channel can have up to 6 addresses, or 6 data pipes as they're called. So basically each unit can communicate with up to 6 other units at the same time. It's a 1 to 6 star network. This unit uses the serial peripheral interface communication protocol. So if you're familiar, there's the different communication protocols. You have UART, you have I2C, you have SPI, which is a serial peripheral interface, the one that this uses. And there's pros and cons to each. SPI's claim to fame is it is fast, and the circuitry is fairly simple. The disadvantage is if you end up having a lot of peripherals, i.e. a lot of different modules or other things on your microcontroller, you require, them to each be wired separately to the Arduino, which can quickly take out all your pins that you have. So you are limited with the number of peripherals you can have with a microcontroller. However, in this case, we only have a few peripherals, i.e. the module itself in this first example, and then we'll be adding, a joystick and some servo motors and stuff. But either way, we're going to be under the limit for pins that we have. So we're going to take the speed that SPI provides. With the module, we can have both bidirectional and unidirectional communication. So bidirectional is if we have the module set up to both transmit and receive. Unidirectional is if we dedicate one module to transmit and have our second nRF24L01 module as a receiver, and which we'll be doing in the first example. Again, the one we're using has a built-in PCB antenna, so it's very compact, this version here, whereas the external antenna isn't as compact, but it makes for much higher range, about 1,000 meters or a kilometer. This shows the pinout. So the ground pin always has this square around it, and that is on the actual board itself, so that you can tell where ground is. VCC, that's your power pin. Again, you want to hook that up to the 3.3 volts on your microcontroller, or if you're using an external power source to power this, make sure it does fall within this voltage range and you're not powering it with 5 volts. Then you have your CE pin. When selected, the module will either transmit or receive. So this basically just is your enable pin. It's called the chip enable pin, and it enables the module to be working, and therefore transmit or receive depending on the mode it is in, which you determine via software, just the coding. You have your CSN, which is your chip select not. When this pin goes low, the module begins listening on its SPI port. So this just decides when the module is actually listening. So this is used, especially you could have, as it said, you could have more than one of these modules a microcontroller is communicating with, and this will allow you to select which of the modules you're communicating with. So the CE pin is active high, whereas the CSN is active low, meaning this one is normally low, and when it goes high, it's enabled. This one is normally high, and when it goes low, it's enabled. And then you have your SPI pins here, serial clock, MOSI, and MISO. These three are your SPI pins. Again, this module uses the serial peripheral interface protocol. So serial clock, MOSI, this stands for master out, slave in. It's used to receive data from the microcontroller. The microcontroller in this analogy is the master, and the slave is the module itself, the peripheral. So the module is receiving data from the microcontroller. The microcontroller is the thing sending out the data. So hence master out and then slave in. The opposite is true for the master in, slave out. It's used to send data to the microcontroller. So again, master in, so the microcontroller is receiving data from the slave, which is the peripheral device here, slave out. Also meant to talk about this briefly, that obviously this nomenclature, master and slave, is quite antiquated and just possibly offensive to people. So I will say that they do have new, as of 2021, there is new nomenclature for this that's been adopted by a lot of the industry, including Adafruit and SparkFun. SparkFun is the kit associated with the Comp44 course. Have pushed for different nomenclature. For example, master out, slave in has been replaced with COPI, which is controller out, peripheral in, because again, the master is the controller, the microcontroller, the slave is the peripheral device. And then MISO has been replaced with CIPO, so controller in, peripheral out. Obviously, a lot of the industry is working towards adopting that. However, this outdated, irrelevant nomenclature is still out there in like a lot of the data sheets and tutorials like this, so I will use it, but just understand that it has changed for the better, so going forward. Last but not least, we have this interrupt pin, which we won't be using, but obviously if you were using, if you, instead of polling, if you're doing interrupts and stuff, you would use that. So again, this just goes over the pins. Again, the ground pin is inside the square. The VCC is your power voltage, and it's from 1.9 to 3.9 volts it accepts, so hook it up to your 3.3 volt pin on your Arduino. Connecting to the 5 volt pin will destroy your module. CE pin, that's your chip enable pin. I'm just going to try to get everything on one screen here. So your CE chip enable pin, again, that's an active high pin, and it's going to either transmit or receive depending on which mode it's currently in, but this allows the module to transmit or receive. It enables it. The CSN pin, again, that's active low, so it's normally kept high and the pin goes low. When the pin does go low, the module begins listening on its SPI port for data and processes. Then we have the serial clock pin, one of the SPI pins, and it accepts clock impulses provided by the SPI bus master, so the microcontroller. So again, the microcontroller is going to ensure that all SPI devices are running off the same serial clock. So this module just accepts that serial clock pulse. And then the master out, slave in, which again has been replaced with COPI in modern days, is basically your SPI input to the module. So again, master out, the microcontroller is sending data out, slave in, the module, which is the slave in this example, is taking the data in. So it's the SPI input to the module, so you're going to receive data from the microcontroller. The opposite is true with the MISO, so the master in, slave out. It's the SPI output from the module, and it's used to send data to the microcontroller. and we're not using the interrupt pin, which would alert the master when new data is available, but we're not using the interrupt. Then we have, it shows the setup and schematic here. I'll just click into it quickly. So the important thing to know about this schematic and the setup for these things is whether you are using the module as a transmitter or a receiver, because again, it can be used for both. It's a transceiver module, but depending which one you're using for, the pin out and the connection is the exact same. So if you follow the connection for the transmitter and receiver, you'll notice they're all connected to the same pins. The power pin, your VCC, is connected to your 3.3 volts on your Arduino in both cases, and the ground pin, which is in the square, is connected to the ground pin on your microcontrollers. You will notice they've got a capacitor across the power pins. That's mentioned a little further down. Basically, it just helps with, again, these modules are susceptible to noise, but power supply noise and different things like that. So this just helps, this decoupling capacitor helps with that power supply issue. So it probably wouldn't matter for our example here because I have this everything like inches apart. Power's not gonna be a huge issue, but I did, if you can tell, I did solder. I believe it's a 10 microfarad. My eyes aren't that great, but a 10 microfarad capacitor across the power supply lines of this module, and I didn't do it on this module, so take that for what it is, I guess. But it would work fine in our case either or. But if you're actually using this for your projects and you want to have the best range possible and to get close to that theoretical value or even extend it, you're definitely going to want to solder in or breadboard in an electrolytic capacitor across your power supply, keeping in mind the polarity. These capacitors are polarized, so this line down here that you can kind of see in the image should be on the ground side. So just make sure you know what you're doing there. All the other pins are connected as normal. The SPI pins should go to the hardware SPI pins associated with your microcontroller. So on the Nano, the master out slave in gets connected to digital pin 11. That's dedicated hardware pin. The master in slave out is digital pin 12, and the serial clock is digital pin 13. And that's the same whether you're using an Arduino Nano or an Uno. It is different on the Mega, so just Google your particular microcontroller and Google the SPI hardware pins. Do you need to plug in the modules, the SPI pins, to the SPI hardware pins on the microcontroller? You don't absolutely need to do it, but the library that we're going to use and uses it, as well as you'll get better performance by doing that. They're designed, the microcontrollers are set up to have those pins as SPI. Otherwise, you're going to have to do some coding to make things work properly, and there's no reason to do that if you have the pins available. So the other pins, like the chip enable and CSN pin, they can just be hooked up to any digital pin. So as you can see, they've been hooked up to digital pin 8 and 9. But the main importance here is that the transmitter and receiver modules are hooked up the exact same way. Okay, just going to zoom in here. But again, just look at that, set yourself up properly, and you'll be good to go. And this just shows the pin out here as well. So I already mentioned this, but we cannot use a breadboard with these modules because the pin spacing is just not enough. So the connection is exactly the same for both the transmitter and receiver, and all the rest of the pin out is just here. Ground goes to ground, VCC goes to 3.3 volt pin. Oh, excuse me. Sorry. The signals generated by these modules are very sensitive to power supply noises, so adding a decoupling capacitor, anything from 10 microfarads to 100 microfarads across the power supply line, is always a very good idea. So again, I think I have 10 microfarads soldered across there, or you could breadboard it in as well. But it says these modules are very sensitive to the signals generated. So just put that in there if you need it. The other pins, again, CSN pin and CE pin, can be hooked up to any digital pins. We've used D8 and D9 in this tutorial. But the SPI pins, which are your master out, slave in, master in, slave out, and your serial clock, should be on pins D11, D12, and D13 if you're using an Arduino Uno or Nano. If you're using a Mega, I think it's like pins 50, 51, 52 or something. You just do a Google search and find that out. Or if you're using another microcontroller, just find out what your dedicated SPI pins are. Now, since the nRF24L01 Plus module requires a lot of data transfer, it will give the best performance when it is connected to the hardware SPI pins on the microcontroller. Note that each Arduino board has different SPI pins, so again, do a Google search and find out. The library that is used with this module is the TMRH20/RF24 library, so you can download that from GitHub at this location, or you can just go into the library of your Arduino IDE and search for RF24, and there you go. The one that shows up by TMRH20 will be available, so just download that and you'll be good to go. I've already downloaded it, so I'm just gonna and then this is going to show the code. So again, if you click into that, it'll show the code, side-by-side code, transmitter, receiver, as well as the output that you're expecting. So on that note, I'm going to jump to the code and kind of go through it with you. So we've got side-by-side on the left here is the transmitter code, on the right is the receiver code. They're very similar, you're going to notice, with only minor differences. And we'll go over that when we get there. So again, I've got, I have the one on the left hooked up as the transceiver, and the Arduino on the right. This module is going to be the, sorry, this is the transmitter, and this is the receiver. My apologies. So on the left, transmitter, on the right, receiver. So the code for both almost identical with a few minor exceptions. In both cases, you're going to have to include the libraries for SPI, so because again, use a serial peripheral interface communication, as well as the libraries for the module itself, nRF24L01, and the RF24 library. So again, you can find those all just by going to GitHub and downloading them, or using the library manager in the Arduino IDE itself. So again, you're going to download the libraries for both your, whether you're using transmit or receiver mode. And then you're going to create an instance of an RF24 module, named radio by convention, but you can name that something else. And you're going to use the parameterized constructor to pass in two ints representing the CE pin and the CSN pin, wherever you have them connected on your microcontroller. So I have mine connected as per the tutorial on pins, these this orange and yellow here, on pins 9 and 8. So the yellow is the chip enable, and the orange pin there is the CSN, chip select not, and that'd be the same on both transmitter and receiver. So chip enable on pin 9 and CSN on pin 8. Now you'll notice I have some other commented out codes here. I've used the same code for both on the Nano and on the Uno and different things, and sometimes based on the project, what I already had hooked into those pins, I had to use different pins, like 6 and 5, I guess, when I had it hooked up once, and 7 and 8 apparently when I had it hooked up to the Mega. So I can see I had it hooked up to a Mega once and an Uno, and so instead of deleting those, I just copied them out, I guess. Commented them out. But that demonstrates very well that, again, the chip enable and chip select pins, it doesn't matter as long as there are any digital pins. And for that matter, you could probably use analog pins in a digital pin fashion. I'm not 100% on that, but I'm sure that would work fine. Then we create, in both the transmitter and the receiver, we create a one-dimensional array of type byte, and we make it constant because we don't want this to be changed. And it just represents the address of how the two are going to communicate. It doesn't really matter what the address is. So in this case, I've made a byte of size 6. So as long as you can use any string of 5 characters as the address. The only importance is that both the address on the transmitter code and the receiver code are the same, and they are. In setup for the transmitter code, we're going to go radio.begin, similar to how you'd go serial.begin, passing in a baud rate, or you go, LCD.begin, or any of the other, like a lot of the other libraries have that begin function. So radio.begin, and then you're going to go radio.open writing pipe, passing in the address as the perimeter argument. So the address that we created up here is 0001. And the fact that it's open writing pipe, that indicates that it is the transmitter code. When we move over to the receiver code, we're going to go radio.begin, and then we're going to open the reading pipe. So reading pipe indicates that it's the receiver. And the reading pipe method takes in 2 arguments. It takes in 0 and address. So that 0 could be anything really. So if I click in here, so as you can see, at pipes 0 and 1 will store a full 5-byte address, which is what we want, and pipes 2 to 5 will technically only store a single byte, borrowing up to 4 additional bytes for pipe 1. But there's a lot of stuff you could read in there if you wanted. Basically, if you put a 0 and 1 in here, it's fine. For this code, it's 0, and that's going to work out fine. And then the address, which is the same address, is your second code. So on the transmitter side, you want to open the writing pipe, passing in the address as an argument. On the receiver code, you want to open reading pipe, passing in 2 arguments, 0 and address, the same address. Then this next on the code, radio.setPA level, that's setting the power amplification level, and it just takes in some constants. So in this case, we passed in the constant nRF24 underscore PA underscore min. That transmits, that gives the minimum level of power amplification. And the more power amplification you give, the larger the range you're going to be able to communicate over, theoretically, because you're going to be using more power, drawing more power from the microcontroller or your power supply to power this module. In my example, the microcontrollers are inches apart from each other, so I have the minimum power amplification, as does the tutorial, because same thing, the controllers are right next to each other. But you could have put max here if this was real world, that way you get the maximum power amplification. So you're going to do radio.stop listening when this is a transmitter, because you don't want to listen, you want to transmit. And you're going to go radio.start listening when this is a receiver, because you want to start listening for the receiver. In the loop for the transmitter, you're going to declare a one-dimensional array of type char, so character array, and you're making it constant because you don't want to change it, and you've just set it to some string literal. I put hello LCD here. I obviously did that because I was using this project for something else that had an LCD at one point, so that's kind of foolish for this example. But anyway, you just send any text string across. Maybe I'll just change that right now just so that it's not so ridiculous. And we could just send across hello world. And so we're going to create a C-style string variable there, so char one-dimensional array. And then we're going to use the radio.write function. So again, we're writing because we're in transmit mode. And we're going to just pass in 2 arguments. A reference, you notice by the ampersand there, a reference to the char one-dimensional array we just created. And we need to tell the module what size of data we're going to write. So how much data we're going to write and transmit. So we put the size of the text in there. So it'll write, it'll write the entire text string. There is a limit. 32 bytes in a single write call is what you can do, but we're within that here. And then we're just delaying for 1 second. We just so we're not constantly transmitting, we're giving ourselves a delay. So the important thing to note here is in the transmitter code, we're using the write function, passing in the 2 arguments, a reference to our char one-dimensional array, and the size that we're going to write. In the loop on the transceiver side, or receiver side, rather, is first of all we're going to check if anything did come in. So if there was any data that was transmitted to us. So we're going to go if radio.available. Again, this is similar to using if serial.available is, if you're looking at using the serial monitor and seeing if someone types something in. We're just checking to see if there's anything available to read. If there is, then we jump in the code here, and we're going to create another char one-dimensional array called text. We're not making it a constant like we did on the right side, because on the right side we just wanted to always send the same thing. On this side, we're going to be using this to store the data we receive, so we can't have it constant. So again, we're creating text, which is a char one-dimensional array of size 32, and set it to an empty string. The size 32 is important because, again, the max that we could get from a write function is 32 bytes, so that's just the max size that we need to make this array. And we set it equal to empty string. That just ensures that we don't have any communication errors, that we don't get any null sort of errors, that sort of thing. So just important to do that. And then we're going to use the radio.read function. It looks almost identical to the write function in the sense it has two arguments. First one is a reference to where you want to store the data that you read in, and the size of where you're storing it. So the size of the data. So again, you're really just replacing the word write with read. And then in this case, we're going to do serial.println. We're going to print the text to the serial monitor. And that's basically it. So that's how the code works. Let's do a quick demo of the code first, just to show you that it does work. So right now I've got nothing hooked up, but I'm going to hook up one side, and hook up the other side. Okay, so I had the previous code on there that had the hello LCD. So you can see that it's transmitting. But so you do see that it's transmitting, but it's hello LCD because it's what I previously had. And let's make sure that keeps continuing. We'll take off the timestamp. We don't need that. Actually, maybe we do, so you know that it's still happening. But let's re-upload these codes. So this one is on pin, not really sure, I'm going to have to unhook one of them. Pin 11. Make sure your board is correct. Mine's Arduino Nano. So I'm just uploading this new code to the transmitter so that it's the new updated version with Hello World and not Hello LCD that was previously on there. And then I'm going to hook up the transceiver, and it was digital pin 21, or port 21 rather. I'm going to upload that code. And so as you can see, the transmitter is sending the hello world, and it's being received on this end by this module, and I've got the timestamp on there to show you that we are continually receiving it every second. So you can see we're updating the seconds, 30 seconds, 31, 32, and so forth. And I'll unhook it from the computer. I'm going to just show you here. If I have so I'll unhook this one end, so the transmitter, and you'll see that the code has stopped transmitting. So we've stopped at 45 seconds. But now I'm going to hook it up to a portable power supply. And you can see we've transmitted again. So again, we're not communicating through the computer. We are communicating through this Arduino here and the module directly communicating with this. Because as you can see, we're not hooked up to any computer, so we are wirelessly transmitting right now and getting that thing. So that's part 1. See my power supply here. So that's part 1, where you're just transmitting text. So the next little bit, I'll just finish reading this off. I know this is a fairly long video. Again, feel free just to look at the tutorial. I'm doing this kind of just showing that, you know, a COM444 student actually doing the code as opposed to just the tutorial, and you know, showing any nuances I noticed, or just kind of highlighting some certain things. So in this code example, the code here on the tutorial is like essentially identical to the code I had, because I just used their code obviously and made some minor changes. But all it's doing is, again, sending a character array from one module to the other. Using a split screen, we were able to show you know, both the receiver and the transmitter code at the same time. You can see that they're almost identical. So on the left is the transmitter code, on the right is the receiver code. But for this first thing, you're sending a character array, or also known as a C-style string. So creating an array, we created an array of addresses. The modules will use to communicate with themselves. The address can literally be anything, right? As long as it's the same on both the transmitter and the receiver. That's the important part. It's how the RF module knows, you know, who they can communicate with. So again, in this example, both code had the address of 0001, but that could have been just any nonsense. Like I could have wrote, you know, Ralph. Is Ralph 5 characters? I don't know. And in the setup, when we were using the difference, I've kind of set up the differences between transmitter and receiver. I've used blue highlight as the transmitter and pink highlight as the highlighting as the receiving code. So in the transmitter code, we used radio.openWritingPipe function, the open writing pipe function, and we set the address to the transmitter by passing in the address as the parameter argument. And that was, transmitter code is used to send data. On the receiving end, we use radio.openReadingPipe, and we pass in the same address as an argument, as well as we had the first argument passed in was a 0 or 1. I used a 0, but either would have worked. But the important thing is, on the transmitting end, we had open writing pipe. On the receiving end, open reading pipe. And the address that was passed in as an argument had to be the same for both. The modules in this example, they were sitting next to each other, so I used the minimum level of power amplification. But again, you could use maximum if you really want to extend your range and you're using this you know, in the real world. So the transmitter code had radio.stop listening function. That set it up as a transmitter. It wasn't going to receive, so it didn't need to listen to anything. It needed to transmit. So we did stop listening. It sets the module as a transmitter. On the receiver module, we did radio.start listening. This sets the module as a receiver to start listening to the transmitter. So the transmitter will send via radio.write. That's how we actually sent data using the write function. And the receiver, on the receiver end, we use the read function, so radio.read. And that's pretty much what that was. We're going to move on to, in the next video, to lighting up LEDs, doing something a little funner than just sending text. But again, remember, this is all part of the Autodesk Instructables tutorial, but there's also, you know, how-to mechatronics. They have their own tutorial, which I've also highlighted. So I believe that's this one. Which, you know, basically says a lot of the same stuff, but you know, you might get a one thing mentioned in this, or that stands out to you a little better. So you know, feel free to read both. If you want me to go through this one in another lengthy and convoluted video, feel free to let me know. But yeah, you can go through all those. Oh, this is remember I said the SPI pins are different depending on your microcontroller. This one shows for an Arduino microcontrollers for the Uno, Nano, and Mega. The Uno and Nano have the same SPI hardware pins. Serial clock is 13, master in slave out is 12, and master out slave in is 11, and your select pin, your slave select, is 10. We didn't use that in this thing. And your mega, it's 50s, all 50s. So 52 serial clock, and therefore so on. This code I've highlighted a little differently as well. Transmitter code is in blue, receivers in pink. But again, I've just kind of highlighted the difference between the transceiver codes. Very similar. Again, CE, CSN. Make sure your pin's there when you create your instance of RF24. On the transmitter end, it's open writing pipe, stop listening, write. Receiver end, it's going to be things like open reading pipe, start listening, if radio dot available, because that's something you have to do when you're on the receiving end. Read and serial dot print. And again, I mentioned the empty strings here. When you set this, is important to avoid communication failure. So again, there's just some differences here. I've done this highlighting might work for me. It might give someone else a headache. Who knows? But this was just for me to be able to quickly see things if I was going through. But both tutorials are really good. This one by How to Mechatronics, or I think might go in a little more detail with certain things, like the decoupling capacitor, maybe why it's used. Again, the RF circuits or radio frequency signals are sensitive to power supply noise. Good idea to include a decoupling capacitor across the power supply line, but they're for the most part the same. So either or, search up How to Mechatronics, Autodesk Constructables, and this one as well. One other thing I will do quickly is, and I say quickly, I know this video is reaching over 45 minutes now, this is kind of a summary of that tutorial I just went through, the Autodesk Constructables tutorial. So I'll go through this quickly here. Again, feel free to stop the video at this point. It's not going to cover anything new. I'm just going to reframe everything in a nice little summary. So, nRF24L01 key points from Autodesk Constructables. So, as you can see here, the nRF module is a versatile RF transceiver capable of both transmitting and receiving signals. It's significantly more suitable for battery-operated devices than traditional Wi-Fi modules due to its ultra-low power consumption and lack of connection delay associated with Wi-Fi modules. It only consumes 12 milliamps, which is less than a single LED during operation. The voltage ranges from 1.9 to 3.6 volts, and the other pins are 5 volt tolerant. It is crucial to power it exclusively with the 3.3 volts from a microcontroller to avoid damaging the chip. Do not power it with 5 volts. The internal antenna version has a range of 100 meters, while the external antenna version can reach up to 1 kilometer, 1,000 meters. Each module boasts 125 different independent RF channels, and they support up to 6 addresses or data pipes. That was that 0001 address we created in the code. So each one can have up to 6 different addresses or data pipes, allowing communication with 6 other units simultaneously. So you can create like a network, a mesh network if you want. Utilizing the SPI serial peripheral interface, the module can handle both bidirectional and unidirectional communication. That's an advantage of SPI. It allows for that bidirectional communication. So basically, later on when we get to the third tutorial in these, we're going to be using both modules as transmitters and receivers. So each module is going to be transmitting sometimes and receiving sometimes to allow for bidirectional communication. The modules feature 8 pins. You got your ground pin, your VCC pin, which you need to hook up to 3.3 volts. Your chip enable pin, which just basically turns the pin on or off, receiving so that it can receive or transmit data. Your chip select pin, or chip select not pin rather. This basically selects this particular module if the microcontroller wants to communicate with this module. You have your serial clock, which is the microcontroller is going to send out and make sure that all of its peripherals, i.e. in this case the modules, are on the same clock, the same pulse signal. That's part of the SPI interface. Then we have the master out slave in, which is the microcontroller sending data out to the module, the master in slave out. So this is the microcontroller receiving data from the module, and the interrupt request pin, which we didn't use. It's important to note again, the spacing of these modules does not allow it to be used in the breadboard. And I say it's vital to connect the SPI pins, serial clock, MOSI, and master and slave out to the hardware SPI pins on your specific microcontroller, such as the Nano, Uno, or whatever, for optimal performance, but it's not necessary. You could use other pins and then just change the code, but understand that the libraries that we use, user must download the TMRH20/RF24 library. That library expects you to use those pins. So optimal performance, use those hardware pins, which are on the Uno and Nano. That's digital pin 13 for the serial clock. Master out, slave in is digital pin 11. Master in, slave out is digital pin 12. The differences in the code structure when you're configuring the module for transmit versus receive modes, the code is pretty similar, except for in the transmit you have stop listening and write functions for transmission, and you have start listening and read functions for receiving data. The different examples that the tutorials go over is sending text, which is the one we've shown in this video, but there's also lighting LEDs based on button presses, or enabling bidirectional communication, which is, we're going to be going back, and each module will act as a transmitter some of the time and a receiver sometime, and the opposite module will be a receiver and transmitter, respectively. And just note that decoupling capacitors enhance the module's performance and reliability. So again, if you want to solder in or breadboard in a 10 microfarad to 100 microfarad capacitor across the power supply lines, the power and VCC pins, keeping in mind polarity, that will help with signal noise and that sort of thing. So it'll just help with the performance of your module. Here I just go over the things again. VCC power, 3.3 volts, ground. Chip enable, again, this is an active high pin. It enables the module for transmission or reception, active high. Chip select not, it's an active low pin. You've got your SPI pins, serial clock, MOSI, and MISO. Interrupt pin we didn't use. This something I looked a little further into when I was really trying to figure out what was the actual difference between the CE or chip enable pin and the CSN chip select pin. So basically I found out that they serve distinct but complementary roles in their operation. The chip enable pin, the CE pin, controls whether the nRF24L01 module is in active mode, like if it's ready for data transmission or reception. It doesn't control if it's transmitting or receiving. It just basically turns the pin on or off, essentially. So it activates the pin, so it enables the pin. So it's important. The chip enable pin is not involved in the SPI communication. It's literally just enabling the pin or not, saying whether this pin is able to accept, data or transmit data. Not involved in SPI communication. Whereas the chip select not pin, the CSN pin, is part of the SPI protocol, and it determines whether the microcontroller is communicating with the nRF24L01 module. So again, it's selecting this chip or not. So it's saying whether or not the microcontroller can talk to this particular module. It is an active low, meaning it's normally held high, and when it's low, that's when it enables SPI communication with the module. So the key differences here is the CE pin, its main role is to control radio operation control, whether or not the radio is operating. It toggles between active and standby modes, meaning when it's not using. And that helps with the power, because in standby mode, I think it was something like 22 microfarads. So very low power consumption, which is why this is the preferred option when you want to do wireless communication and you want to have battery controlled microcontrollers. So this is your logic, your application logic. Your CSN pin, that uses the SPI communication protocol. That's its main role. And it enables or disables the communication between the NRF module and the microcontroller. So it's chip select, whether or not you're controlling. So this is kind of a little analogy. Think of the chip select not as a doorbell that lets the microcontroller notify the nRF24L01 module when it wants to talk to it. So the CSN is the doorbell that says, hey, the microcontroller says, hey, I want to talk to you. And that's what its job is. Whereas the chip enable pin, on the other hand, it's just a power switch that decides whether the radio is actively transmitting or receiving or staying idle. So it's the on-off switch. Mode of operation, whether you're transmitting or receiving, it's software configuration. You're controlling that in your code. So whether you're transmitting or receiving, that's based on whether you're listening, stop listening, you're transmitting, start listening or receiving. So, that sort of thing. So it's your code that is doing that. So the mode of operation, transmitting and receiving, of the nRF24L01 is primarily controlled by software configuration, not directly by a specific pin. However, the CE pin plays a crucial role in enabling the radio for transmission or reception after the desired mode is configured via SPI. So here's how it works. We won't go over this. This is how it's working behind the scenes, but the library takes care of this for you, so you can just use your write functions and read functions. This is the main summary here. The SPI config register. This is the main summary of this, which you don't have to worry about. But basically, the CE pin activates the selected mode, whether you're going to be able to transmit or receive or not. If you're on or off, it's a power switch. This is just saying that it's highly recommended to connect the module's SPI wires, i.e. its serial clock, MOSI, and MISU pins to the dedicated SPI pins on the Arduino. Not absolutely, it's not mandatory, but it is going to help with your optimal performance. So optimal performance, compatibility, because it's what the RF24 library is expecting. Again, it's going to be faster than bit banging, which is just manually, emulating the SPI in software. So just if you have the pins available, use them. On the Arduino Uno and Nano, again, these are your SPI pins: master out, slave in, pin 11, master in, slave out, pin 12, serial clock, pin 13, and then your CSN and CE pins can be any digital pins. Use hardware SPI pins. This is the easiest and most reliable way. I understand a lot of this information is redundant, but that's a way to remember things, right? The terms master out, slave in, and master in, slave out were officially replaced with more inclusive and functionally descriptive names in 2021. I believe I alluded to this earlier in the video, that the master out, slave in, and master in, slave out, that nomenclature is incredibly outdated. So we have replaced that recently. The reason I still use the other nomenclature was because it is still going to be in those tutorials specifically, and a lot of other information that you're going to find out there. So I wanted you to know it, but understand that there is better nomenclature out there that's more updated and not offensive to anyone. So master out, slave in has been replaced with SDO, serial data out, or COPI, controller out, peripheral in. So this indicates that data is going from the controller, master, to the peripheral, slave. And the good thing about this nomenclature, besides it's not offensive and it's just more updated and more modern, is that it is more descriptive. So by saying controller out, peripheral in, that's really explicit to what it's doing. Oh, the controller is sending the information, the peripheral device, in this case the module, is receiving it. Because with the whole master-slave, if you're not familiar with this nomenclature as far as computers go, do you know that the master is the microcontroller and that the slave is the module? You may not. This is pretty explicit. The controller, you're probably going to realize that's the microcontroller. The peripheral is going to be this peripheral device. So, and it's just not offensive. So there you go. The master in, slave out is now called the SDI, so serial data in, because again it's master in. We're always referenced to the controller, so the serial data in, or CIPO, controller in, peripheral out. So again, the controller is receiving the data, and the peripheral, i.e. the module, the nRF24L01 module, is outputting the data. This indicates the data is going from the peripheral to the controller. And then the slave select is now called chip select pin. So it was called the slave select. Chip select, same thing is happening. It describes the pin used to select the specific peripheral being communicated with. Especially, this is important when you have more than one peripheral device being controlled by one microcontroller. Using SPI, you have to select the different pins to be on and off. And then serial clock, that's unchanged. Clocks were never offensive to anyone. So And serial just indicates the way the data is being transferred. It's being transferred serially, in a sequence, not in parallel. So again, the reasons for the change, it just removes the connotations tied to historical injustices, and the new terms describe the data flow more explicitly. So COPI and CIPO, that's controller out, peripheral in, and controller in, peripheral out. It just very clearly indicates the direction that the data is moving relative to the controller and the peripheral. The controller being the microcontroller, the Arduino, and the peripheral being, in this case, the wireless module, the nRF24L01 RF transceiver. And with the systems becoming more complex, another reason that it's good that we're going to this modern usage is systems are becoming more complex, so the concept of master and slave is less applicable as roles can change dynamically. A lot of now new technology, one piece of hardware, one module could be the master sometimes, the slave other times, or the controller sometimes and the peripheral other times. So it's becoming less of a, hardware is becoming less dedicated where this is always the controller and this is always the peripheral. So, and just a note, Adafruit and SparkFun had had a part to play in updating this nomenclature, and I just mentioned that because I'm part of COM444 through the Arduino, or not through Arduino, through Athabasca University. I'm taking the COM44 course, and SparkFun is the kit that we're using for this course. So just thought that was a nifty note. And then older documentation, but again, why did I keep using the master out, slave in, or master in, slave out terminology, despite that it is possibly offensive to people, which is not my intention, is because the older documentation will use it. So many legacy data sheets and resources, i.e. all of the tutorials I showed you, still use the MOSI and MISU terminology. So the master out, slave in, and master in, slave out terminology. So that's why I used it for education purposes, so that you understood the tutorials and I wasn't just talking more gibberish than I already probably am. But understand that there is better terminology out there, and so it's good to know both. So one, that day, as soon as we all are familiar, we can update these tutorials, update all the documentation, and get rid of this old, antiquated, offensive nomenclature for the better, copy and CIPO. Anyway, that's it. I know this has been a long video. If you've stuck with it, thank you. And if you have any questions, post it on the forum.